Hello, everybody. My name is Masood Olia, and I'm a professor in the School of Engineering at Wentworth University. And I'm here with a problem related to the subject of vibrations and to topic of an underdamped system. So I want to just give you some background and tell you about different how you can get the differential equation of the system, and then I'm going to give you some initial conditions to figure out the solutions to this differential equation. So let me go ahead and close my, sorry, just want to get rid of this. There we go. And then I'm going to flatten my iPad. Sorry for the noise, excessive noise. All right, so here we have a mass of 10 pounds. So the weight is actually 10 pounds. We have to be careful with the unit here. And you can see we have a damper here, which is usually denoted by C, and say K1 here and K2, two springs with a given stiffness. Now, in general, if we have some mass and what we call an equivalent spring, an equivalent damping coefficient, an equivalent mass, right? Then you can find basically the differential equation of this. If you give it, say, a disturbance of y, either up or down, doesn't matter. So as you know, the differential equation becomes mass equivalent times y double dot. That's basically mass times acceleration. Plus C equivalent y dot plus K equivalent y equals 0. So this is actually free vibration, so there's no forcing function, force that generates the vibration. So the disturbance is done by pushing the mass down or up, then maybe even give it some initial velocity and let it vibrate. So now, look, guys, the mass equivalent here is basically the weight. There's only one mass, so that would be the mass equivalent. See, these two springs are actually parallel. So when this guy moves down with y, this is stretched by y, and this is compressed by y, right? So they're actually parallel. So two parallel springs are K equivalent becomes basically K1 plus K2, right? So in this case, we have an 80 pound per foot and 60 pound per foot. That becomes 140 pound per foot. And there's only one damper, so your C equivalent is what we have here. The unit is pounds second per foot. All right, so our differential equation therefore becomes mass equivalent, which is this guy, 10 over 32.2 y double dot, right? Plus C equivalent, which is 5 y dot, and then K equivalent is 140 y. Now we can normalize this, guys. Normalizing it basically means divide by this number. So if we do that, we end up getting the following: y double dot plus 16.1 y dot plus 450 point roughly 8 equals 0. So you see, the general equation, guys, can be also written in terms of these properties like natural frequency and the damping ratio. And basically, the differential equation, either in terms of y or x, doesn't matter, is basically can be written like this. Sorry, omega n squared times y. So you see, this is actually the 2 zeta omega n, and this is omega n squared. Omega n, of course, is natural frequency. And the damping ratio, the zeta, so this is natural frequency, and the damping ratio basically is the ratio of C divided by 2 square root of Km, which actually, or defined like this, we can write it as 2m omega n. So So basically, you can go ahead and find your natural frequency. So your omega n squared is 450.8. Therefore, omega n, which is the natural frequency of the system, is going to be 21 square root of 450.8, 21.232 units of radians per second. All right. And then our zeta then, actually, if you try to figure it out, either using this, right? You could use that or just the same thing that you see here. Doesn't matter. In fact, let me just use that notation, that 2 zeta omega n is equal to 16.1, and then plug in for omega n, right? So zeta, just make it more like, look like that symbol. Zeta should come out to be about 0.379. Now, from other videos that you probably have seen, this is obviously a ratio, it's dimensionless. If zeta is less than 1, the system is underdamped. So it's going to oscillate. And for an underdamped system, the general equation, guys, for the solution y or x is some constant a e to the power minus zeta omega n t. It's a combination of sine and cosine with some amplitude, but we could actually make it one sine wave, actually, and write it like this: sine omega d times t plus some phase angle phi. Now, omega d is called the damped frequency, and it can be calculated like this. So if you go ahead, put the omega n and the damping ratio in this equation, your damped frequency is always smaller than your natural frequency, obviously, because of damping. So it comes out to be equal to, let me see, I have written it down here, 19.647. And that's radians per second. And then if you want to know what is the damped period, you just take 2 pi and divide by omega d. So 2 pi divided by 19.647. So that means that this oscillating sine wave keeps repeating itself every 0.32 seconds. So then the question is, how do you find A and phi? A and phi, there is a way to do it. It's based on the initial condition. So let's say at t equals 0, we are told that we have certain x0, certain y0 initial displacement, since I'm using the y notation, right? And some initial velocity, which is actually the y dot. And I'm going to give you some values. For example, I'm going to give you 7 inches for this guy. So if we basically move this guy 7 inches, move it down, and give it some initial velocity, let's say of 150 inches per second. So you only need basically one initial condition to start the oscillation. But let's say you have both initial position and initial velocity given as it is, right? So A, it can be shown that, and I have probably shown it in some other videos, you can check on that, that A becomes, in the denominator we have omega d, and then the numerator becomes combination of 2 terms here, which involves initial velocity and initial position. Usually you call this x0. So let me just use that notation. Okay. Sorry, guys. So x0 or y0, the same thing here. Because the formula that I have here is in terms of x0, which is more general. All right. Zeta omega and x0 squared, which is 7 inches in this case, plus x0 omega d squared. So remember, radical is only on the numerator. If you go ahead and plug in for V0, you plug in 150 inches per second, and for x0, you put 7 inches. And by the way, as long as you're consistent with the unit, you don't have to change to feet per second or feet. What you get out of this is in inches then. And that would be, looks like it comes out to be 12.62 if I'm not wrong. All right. And similarly, this phase angle, right, would be determined. It could be shown that it's really the inverse tan of x0 omega d in the numerator, basically this term divided by this term, v0 plus zeta omega n x0. So if you go ahead and plug in all the numbers that we got, the damped frequency, natural frequency, and x0 and v0, right? Meaning, 7 inches per second and 7 inch and 150 inch per second, your angle becomes, phi becomes 33.68, or almost 33.7, which has to be converted. So multiplied by pi over 180. Usually in this equation, it has to be in radians. So that's about 0.578 radians. So the final form of the equation, y as a function of time, is going to be a, which is 12.62, right? E to the power minus zeta, which is 0.3. Let's see, zeta was what? I lost my zeta, 0.379 times omega n, which is 21.232 t, and then sine of omega d, which is 19.647 t, and then, as I said, phi has to be in radians. So this is the equation that governs the motion of this. How does it look like, guys? You probably have seen it in a video. If you plot y as a function of time, basically you have some initial, let's say this is in inches and time is in second, right? So you have some, let's say 7 inches, let's say that's for 7 inches, and you have some initial velocity. So it's going to look like this. So basically you have an envelope like this. That envelope actually is represented by this guy. So that's the envelope, this exponential envelope. And you have a sine wave which is dying within this envelope. And what I showed you here, by the way, this 0.32 seconds is the distance between the peak to peak here. So that's the damped period, guys, which happens to be the 0.32 seconds. All right, guys, I hope you enjoyed this video, and I'm always coming with new videos. As always, I appreciate if you like the video and subscribe to my channel. Thank you, and see you soon.